Okay, we have here an example of the use of the response spectral curves or graph by simply predicting the displacement, velocity, and acceleration of a single degree of freedom system. No? So, a structure modeled as a single degree of freedom system has a period equivalent to t equals 1 second, and we are asked to use the RSM or the RSA to determine the maximum absolute acceleration, relative displacement, and relative pseudo velocity. Okay, so I'd like to point out one thing about why this is absolute. Okay, for displacement class, for acceleration, I mean, the reason why we are talking of absolute acceleration because the mass is always the basis, for your force. Okay, so this is now your axis, let's say absolute y coordinate. Okay, so the mass is simply giving you a force, reverse effective force, which is equivalent to a simple formula by Newton, which is mass times acceleration. And acceleration is simply y double that. Okay, so where a is simply y double that. And this is an absolute acceleration. Okay, but when we talk of spring, so making sure that this is also your x motion. Okay, your spring will be attached to the coordinate x, and of also you have a damper here. Okay, so your k and your c is attached to both x and y. That's why here you have a relative u is equal to y minus x. So this must be relative displacement and relative pseudo velocity. The word pseudo was inserted because, as I've told you, the analytical values does not jive with the experimental. So it's a pseudo velocity because it's a false velocity. It does not represent the actual velocity. So I have to have correction factors just in case you want to use the design spectra. Um, you have to know the factors involved, and the code takes care of it. Okay, so the code takes care of the error. Okay, that's why we have codes to follow. Okay, so remember that, no? Okay, so a foundation motion equal to the ns component of the L-center earthquake 1940 will be considered, and for letter B, the design spectral earthquake with the maximum ground acceleration of 0.32 g will be considered, assuming, of course, your lambda. So this is now the damping ratio kasi, or sometimes I use the lambda there. Okay, so dito ang gagamitin natin yung ns component of the L centro figure 5.8. Okay, so let's look into figure 5.8. Okay, so here's the figure. Okay, so the figure 5.8, we choose the 10% dumping. It's not as clear. Okay, so this is the 10% damping, and ang ating period, ang ating uh, frequency is 1. Okay, so frequency natin 1. So dito tayo, we mark it, and then we go up and strike the 10% damping. Okay, and then from here we set our straight edge to get the uh, okay, we set the to get the corresponding, okay, a graph on the displacement. Okay, so this is the displacement class. This is the displacement curve there. Okay, and you can read it between 2 and 5. No, but this is logarithmic. It's really very difficult to calculate by simply looking at it. So the division of this is not equal. So as it goes upward to the left, the subdivision becomes smaller and smaller. So maybe uh, in between 2 and 5, this is not uh, 3.5 or 3 less, no? So this is your 3 is somewhere there, no? Mas malayo pa siya, no? So if I will look at this, is this safe to say that this is less than 3.5? More or less it can be 3 point something or 3 or less than 3. Okay, so I don't know how to really if you want, you can subdivide this into a logarithmic scale from 2 to 5, and that's very difficult, no, if we do it now. So what we are going to do is roughly it's more than 3 or less than 3, so something like that. So we check our answers later. Okay, so let's just mark it there, and then for the displacement, sorry, velocity, I again okay, use my mark, and it's less than 20 there. Okay, so I'll use a, okay, it's less than 20, and for the acceleration, uh, I have here, okay, it's between 0.2 and 0.5. So again, this is 0.2 plus 1.5 is 0.35, so it must be greater than 0.30, but not greater than, it must be, but less than maybe 4. Okay, so greater than 0.3 but less than 0.4. So let's look at the answers now. So let's write it. For the displacement, we have around 3, okay, plus or minus 3. This inch per, or inches. Okay, for the velocity we have less than 20, and for the acceleration we have around greater than 0.30. Okay, so let's just look if we're close to the answers. Okay, so 320.3. Okay, so this is 3 Okay, I'm a little bit close, no? This is plus or minus 3 or 3, less than 20, and greater than 0.30. Okay, so roughly that's okay. Okay, of course, acceleration is normalized to 1g. Okay, so you have to multiply it by g. So from the basic design spectra, let's use figure 5.9. The same 1 CPS 10% damping and a scaling factor of 0.32 g maximum ground acceleration is used. Okay, so there's now a scaling factor of 0.32 for figure 5.9. So let's take a look at figure 5.9. Okay. Okay, so the first figure I'd like to tell you that this is not a normalized response spectra. This is an actual response spectra here. Okay, only the g-force or the acceleration force is actually normalized at g here. So if you look, this is point, okay, point 1, point 2, and so on. But for a design response spectra, which is normalized, all all the values you will be getting should be multiplied by a factor, okay, the scaled factor. So let's attempt to check a 10%. Okay, so where's the 10%? The 10% is actually the first graph here, which is uh, already normalized. Okay, already normalized from this curve. Okay, so let's take a look. So this is now your 10% graph. Okay, so this one. So can you see this line here? So this is the graph that we are talking to there. So I showed you how to normalize this a while ago. Okay, for different dumping. So let's check now which is at 1 CPS. Okay, so dito tayo medyo magde-drop. Ayan. So this is now your 1 CPS. Okay, so this is your point. Okay, and then if you are going to look at the displacement, first the displacement. Okay, so approximately, it's not a perfect. Okay, so if I'm going to look at the displacement, it's actually almost exact, no, on the displacement axis. Okay, so it's more or less 10 here. Okay, so let's write it. Displacement is 10g. Okay, and then your velocity is horizontal, upward to the left is the displacement. Then horizontal is the velocity, so you get 50, more than 50, no? But this is, I think, less than 75, no? So V is between 50 to 75. Of course, you have to multiply this by g, and the acceleration okay, so the acceleration is at this graph at this point. Okay, so this is more or less 1 2.5, and then can't see this, it's 1. Okay, so it's less than 1 g. Okay, so less than 1 g. So acceleration is less than 1 g. Okay, so let's look at it. The answers now are okay, 10 g, so quite near. Okay, between 50 to 75 and less than 1 g. Okay, so that's the way how to uh, okay, to use the design spectra in figure 5.9. Okay, so in Baguio, I noticed that their acceleration is very close to scaling. No, scaled acceleration, the peak ground acceleration is actually 0.30 to 0.30 to 0.35 g. You know, so in Tarlac, I'm using 0.20, but somebody told me that it's safe to use 0.30 as your peak ground acceleration, um, kahit na medyo hindi wala ka dun sa ganong lugar, like sa Baguio kasi na-amplify nung height nung terrain nila, no? Yung acceleration kasi nasa taas daw sila. Okay, I really don't know the basis for it. I think this will answer the question, our next topic on the influence of soil. Okay, the soil type is the basis for your response spectrum. Okay, so I'll discuss this on the next video. So for now, that's it for the sample problem.